made of slate and the sides are made of glass. The slate costs 5 times as much as glass. Find the dimensions of the aquarium that will minimize our cost. So it sounds like a typical Calc 1 problem, except we have more variables than the problems they give us in Calc 1. In Calc 1, they give us more constraints so that we could reduce it down eventually to 1 input and 1 output. Here, they're not doing that for us. So my original function, so my f of x function is the, actually it'll actually be a 4-dimensional function. It'll be the volume, so x times y times z is the volume of the aquarium, and I guess you have to decide what you're going to use for x and what you're going to use for y and what you're going to use for z. So I will let y be the one side and x be the other side, and then z is the height of it. So we know that 5 times xy okay, xy is the area of the body. So let's just say that the glass cost 1 unit, okay, so 1 unit of money per square, do they give us? Yeah, per unit area, yeah, so I'll just say per unit area. So per square inch or whatever. So the slate is 5 times that, okay? So I know they don't give us any dollars, okay? They just tell us that the base of it costs 5 times as much. So 5 times its area is going to be its cost when you compare it to the cost of the glass. So I have 2 sides of glass that are y times z, and I have 2 sides of glass that are x times z. So again, I know I don't have any dollar amounts in there, but if you make the glass 1 monetary unit per area, then the bottom is going to be 5 times that. So this is my constraint function. Oh, actually, this is my constraint. This is my function I'm trying to minimize. Because they said that it equals a set volume. So this is set. So this is my constraint. And then this is what I'm trying to minimize. So again, the front and the back were y times z, and the 2 sides were x times z. It's an aquarium, so it doesn't have a top. I'm assuming. So I'm not putting a top on it, but okay. So the air has to
Gotta get the fish in.
mix in with the water, so even when you have a top, there's like a little bend. Okay, so our cost is our original function, our original surface, and the volume is our constraint. So the V is some constant, they didn't tell us the constant. But we want to treat it like it's a constant. Okay, so delta cost will be plus 2z. Is everybody with me on where I got that? Because I've taken the derivative with respect to x. And then with respect to y, 5y plus 2z. And then with respect to z, it'll be 2y plus 2x.
Shouldn't the first one be 5y plus 2z?
Yeah. And then delta of our constraint, so delta B, I'll just call it delta B, is y, z, and then with respect to y over the x, z, is xy. So then delta cost needs to be parallel to delta B. So 5y plus 2z has to equal some constant times yz. And 5x plus 2z has to equal some constant times xz. And 2y plus 2x has to equal some constant times xy. Yeah, I guess so. You know, I'm doing the little trick of setting them all equal to lambda, and I might step back for a minute and see if it's not a quicker algorithm for us to do with this one.
Oh, I see something beautiful there. The left two, so you can say
Okay,
5,
Robert, just a second, because I was in the middle of thinking of something else, okay? If, I actually do want to show you this one other trick. What I did here would work, I mean, you could set these equal to each other, and then if you set these two equal and cross multiply, you'll get something that you can work with, and then you plug that into these two. But there's another little trick that sometimes comes in handy, and this is an example where it would work. So I want to show that to you. Notice how this has lambda y and z, this has lambda x and z, this has lambda x and y. If I multiply this equation all by x, and then I multiply this equation all by y, and then I multiply this one all by z. Okay, so I multiply, it's like what I did was legal because I multiplied both sides of this equation by the same thing. I multiplied by x. I multiplied both sides of this equation by y. I multiplied both sides of this equation by z. That's all legal to do. But by doing that, notice that they're all equal to each other. And so you could save, basically we're saving the step of setting up the ratios and then doing cross multiplying. Like we're accomplishing the same thing without having to do the extra step of setting up our ratios. Okay, so if I then set, okay, see lambda xyz equals this, but lambda xyz also equals this. So if I set those two equal to each other, let's see see like these can cancel out, and then the 2's can divide out, and the z's can divide out. And so x has to equal y. Okay, again, you know, not surprising. And then if I do the same thing with any of the 2 others, I mean, I normally just pick the 2 that are next to each other, but I could also pick this one and pair it with that one. And these cancel out, and the x's cancel out, but this time I get 5y equals 2z, but remember x equals y. So this also means that 5x equals 2z. So z equals 5 halves the others. So x and y are equal to each other, and z equals 5 halves of x, which is also equal to y. Okay, so again, that's just a little algebra trick that sometimes comes up. What you look for is your different equations have the 2 of the variables paired. And so then if you do what I did, like this equation needed to be multiplied by x, this one needed to be multiplied by y, that one needed to be multiplied by z, then you kind of shave off a step of having things to set equal to each other. All right, so after we like do whatever we're going to do algebraically, then we take that and we plug it back into our constraint. Okay, so my constraint was that the volume is fixed. So x and y are the same, and z is 5 halves of whatever it is. And so 5 halves x cubed is my volume. So that gives you a formula for the maximum volume. And I don't, I'm trying to, like we might not get it anymore. So basically we know that our base has to be a square, so our x and y would be the same, and then z would be 5 halves of whatever that is going to give you, sorry, we're trying to minimize our costs, so this should give you minimum cost. So how we would test that, I don't know, you could make up some points, plug them in, or
Well, it said in our.
well, okay, hang on, I'm trying to, so, okay, so this is, okay, so this is giving us our volume, but then we're trying to minimize our costs, so, and we know, I guess we might as well also come up with a formula for the cost cleanup. So x and y are the same, and so I'm just gonna use x everywhere there's an x or a y, and then z is 5 halves of whatever x and y are. And I get, it looks like we're gonna get 15 x squared. And then our cost function. Is it? Is it that clean? Is it really good? Yeah, I think there's nothing. I guess because the volume is supposed to be fixed, like given given this problem, the volume was going to be some number. You could also replace the X's in terms of B, because we know that the volume is equal to this, so that means that 2/5 B is equal to X cubed, and so the cube root of that is X, so the last little thing you could do is go over the cost and say, well, if I know my volume was, 1,000 cubic inches or whatever it might be, then that's probably the best final form of it, because if you know that your aquarium is supposed to hold a certain volume, you could just plug the volume into that formula and it should give you the minimum cost.